They don't even get to call themselves 16s. Yeah. It's on time. Lost by, God, Wichita State almost won the first game last year.
Oh, last year, yeah.
And then Oregon State almost tripled their scores. Oh my God, their freaking wins. Paul win, which is like a D2 at most. It's like D3. Never heard of that. They lost to that. I've never heard of that.
They lost to the Indian logos with non-divisional teams.
Yeah.
They lost to a Division 2 or 3 team.
Lemoyne,
They beat you. Oh, they beat Alcorn. There you go.
twice.
Alcorn State. Ooh, wow.
Okay, we'll go with Lemoyne or Smith is. They lost to an NAIA.
You gotta be kidding me.
They only have 4 students, 4 sports, and total of 45 student athletes.
I know that Courtney has practice testing for that. Maybe that affects Annie too. I'm not quite sure the others are. Hattie is auditing the course, so she's come to a lot of it. Probably will come back later, but as things are heavy, she she has that option. So this might be it. So we're going to go ahead. Nice to have you here. We're going to continue looking at times here. And homework is due on Monday, so the others can get the notes and the integrity to look at there. And we talked some about time series, looking at examples and how it can affect things. The standard error for an average is affected by the correlation. So the simple formula of S over the square root of N, standard error, doesn't really work. The actual standard error when the measurements are correlated would be much higher. So we can do an adjustment there. We can also model the time effect directly and look at residuals. And there's a way to do something called filtering on those, on the variables to adjust, to kind of take out some of the effect of a first order autocorrelation and then be able to test for effects without that impact. We'll also look at a couple quick ways to test if there's not a correlation or not. Yeah. So in this, modeling the time effect, we have our y sub t variable, and then time is just given by t. If there's a linear change in time, we could model the y sub t, given t, as a linear function of time, and that would just say that it's growing. Right? Alternatively, you could have other functions of time, beta 0 plus beta 1t. You could have time in there as a square. So if things were going up quadratic or leveling off or changing like that. Right? And so we could fit a model that has some time effect or other variations on this with least squares. And fitting least squares, we can use our LM commands. We can do analysis of variance. We can look at diagnostics to see if that seems to be the pattern. And say for the second model here, we're going to get estimates like that. Right. So alternatively, we might have a variable other than time that we think is possibly more related to the y's. Time could still be a factor, right? We might have some variable x that's varying in time, right? So we could just fit, a model that says, just an ordinary least squares model, maybe with a square in there if things are going kind of quadratic. I guess I don't need this little hat over here, right, to write out the model with the residuals at time t. Right. We could use least squares and get estimates of the coefficients there. But then the question is, what impact does the correlation over time have on the standard errors? We could get significant effects of time or of x coefficients when we run the ordinary linear regression, but we know that if the observations are correlated, they're not independent, and so the standard errors wouldn't be accurate. Right? So what we can do is we can do an adjustment to that. So we are going to do something called filtering. Right? And so we're going to get new values of y and x. Right? And then run the regression of those. And we're going to do this in a way so that the standard errors that come out of this one are more appropriate. Right? These will have, so we're going to model y, the new y's versus the new x's, and then the slope coefficients will be correct. That we get will match before, match those that we would get with the previous models, doing the y on x directly. Standard errors will be adjusted, right, for the autocorrelation. So we can better judge significance and make confidence intervals like that. Right? And so the filtering is to take, if alpha is our auto correlation coefficient, autoregression coefficient, that's what it's called. So the mean of y is related to the mean of the previous one by that multiplicative factor. We're going to create two new variables, v sub t, which is going to be our y sub t minus alpha times y sub t minus 1. How does the average of y sub t change? Well, it's related to the average of y sub t minus 1 with this multiplier on there. So we're going to take out that difference, take out the correlation there. We're going to apply that same transformation to the x's. And then we're going to regress, we're going to regress v sub t on the u sub t. And the coefficients that we get will be the same as if we had regressed y on x. The standard errors will be different. So the slopes are good. So we're going to be fitting a model that the mean of t in just a linear case is, if you just do this filtering and you fit a regression of v on u, the beta is the same as if you just regressed y on x. Right? The slope is going to be, the intercept is going to be different. Right? The relationship, I guess I can get it over here, the alpha 0 relates to the this intercept times 1 minus alpha. So you could get an estimate of the original intercept here from the filtered regression by dividing by 1 over that. Right? But to do this, we need this alpha autoregression coefficient. Right? So we're going to estimate that from the residuals of fitting the y on x model. We're going to fit y on x, get the residuals, and use that to look at the autocorrelation. Because we're really concerned with the autocorrelation in the error terms of the model. We don't, the epsilons are no longer independent when they're related, right? So to implement this, right? So to implement it, we're going to regress y on x, and and get the residuals from this. Right? And we're going to calculate C1, which is 1 over n minus 1, the sum t going from 2 up to n of the residual at time t times the residual at time t minus 1. And our c sub 0 is 1 over n minus 1, going from 1 to n of the residuals at time t squared. So a variance of residuals and a covariance of residuals. And R1 is going to be the ratio of these two things. That's our estimator of alpha. And with that estimated R, then we're going to filter. So we're going to let V sub t be y sub t minus R1 times t minus 1, and U sub t is going to be the x sub t minus R1 x sub t minus 1. And then we're going to regress the V sub t on the U sub t and assess significance of the slope based on that. Right? From this, we do inference for beta 1. So if we are dealing with an AR1 model, then this will give proper inference for this, and we should be able to do significant testing. Right? That's one predictor, but you could generalize this to more predictors. So if you had several x's, you could regress y on x, all the x's, get you had a bunch of x's, you could regress y on a bunch of x's and get residuals. And then estimate R1 from those residuals. And then adjust y, and then adjust every x that you have, multivariate, like this. Right? And then regress the V sub t on your collection of U sub t's. And then you can do inference for a bunch of different slopes. Right? So it works that way. Right? If some things are squared, so you could look at time effects too. X could be t for time. So you could be, what's the impact of time over time? Is it changing? Is there a quadratic change? Is it accelerating? You can look at that too, right? If you are looking at quadratic things, so if you have, t squared, t cubed, etc., or x of t squared, x of t cubed into the model. So the book makes a point in looking at these effects, particularly for time. Often time is recorded in large numbers. The year, like 1982, 1983, 1984, those are big numbers. And taking a square t and t squared of those big numbers, well, out there it's pretty highly correlated, right? Or these things could be in decades or centuries or something like that. And so if these are large numbers and you try to regress on those, you run into a multicollinearity problem. Right? So the general, instead of regressing on those, you might replace those in this before ever doing any filtering, just by t, that's supposed to be mean, E-A-N, right? So the average of the t squared, t minus the mean of t, right, cubed, etc. The point of this is that the time and its squared deviation from the center won't be as correlated. Right? They won't be very correlated at all, right? In fact, and so you could have these different predictors in there that would show different effects. Right? Dates in particular. So if you had a bunch of, one example we'll look at has dates, going kind of, and there's projections out to 2050 or so out there. The actual data set, of course, doesn't go out that far, but we're kind of, it starts at 1850, going every year, and you're thinking about projecting out there. You could subtract the mean from the times, but you're subtracting something like, 1912.3. Right? So it kind of is a funny, 0.5 or something. It's kind of a funny thing to subtract. I think that you could modify variables to have kind of a convenient reference point, right? You could take t minus something like 1950 and square that, and t minus 1950, cubed as you go through that. So it won't be exactly the mean, but it's kind of an easy thing to think about. What is the difference of the year from 1950 or some other reference point, right? Some economic time series, there's kind of a reset every once in a while on some economic things, and they kind of have this cut point. What is it before or after? And that's kind of a convenient reference point to do that. It's easier to communicate a number versus some arbitrary mean that doesn't really apply to other things. Some things are in time, really are, scale, like here, the 1800, the 2000, aren't so critical for modeling. You might make it 50, start at, you might make this 0, and so on, or take out the first few things, so it's kind of years since a time. And then it won't be such large numbers to deal with. We'll kind of see some application of this as we try to do some modeling. So if you want to regress to see if some x's are important in predicting something, the filtering can get you better assessment of standard errors. Right? But before going to some examples, right? Before you would do this, you might say testing for some type of autoregressive structure. Right? Is there a significant autoregressive feature that you might want to adjust for in the residuals? Something might be based on time, but if it's kind of independent observations every year, you wouldn't necessarily need to do this complex work. And then other things, you might not really know. You might have a spatial structure where you kind of put things in some type of order. And is there time of an association over that spatial order? Well, maybe there is, maybe there isn't. If there is, you might use these techniques to do an adjustment for that. Right? But if it's not there, then you might need to do it. Right? So one way to test, we can fit a model to predict y. And we're going to store the residuals. Right? And we're going to compute, based on those, our lag 1 correlation. Now it turns out that if n is independent, if the observations are independent, and n is large, the book says more than 200, but maybe it's not that. Oh, it says 100 actually, I think. So that you would kind of need a fairly long string, like daily data or frequent data. Right? Then this R1 can be figured out to be distributed approximately normal around 0, correlation 0, and its standard deviation is like 1 over the square root of n, or standard error. Right? So if that's what it is under the null hypothesis, we could look at our actual statistic times the square root of n. So our test becomes z is this one times the square root of n, and then this thing is like a standard normal. and we would reject a correlation of 0. Our autocorrelation of 0 if our z value is bigger than some cutoff. So this is rejecting at, now here's a different alpha significance level. If the normal deviation is far enough away. And in most of all of our cases where we saw a fairly appreciable correlation and we're getting correlations 0.5, 0.4, something like that, the series were not short, and so they would surely reject that. So it doesn't seem like a very, so in our cases it's going to clearly say that there's independent, they're not independent. And if it wasn't, if the sample size wasn't so big and we didn't want to use normals, there might be a bootstrap type test that we might use. We're not necessarily going to go into that, but if you could resample your data under the assumption that they're independent, that the residuals are independent, and you calculated the same statistic for bootstrap samples, you could look at the distribution of those in comparison to this one, or just R1 by itself, and see if your observed statistic is far outside of what would be consistent with independence, right? But there's another test called a runs test that works even if, for small sample sizes. And so on this, we're going to fit a model for y, to predict y, and we're going to produce residuals, or E sub t residuals, right? And we're going to look at the sign of those residuals. Are they positive or negative? Or some test looks, are they above the median of the residuals or below the median of the residuals? In observations, let's say we look at the sign, right, positive or negative. A version that R does in one of these packages looks at E sub t minus the median of the E sub t's. This tends to split things into an equal division, half the residuals above the median, half below of it. But the idea is kind of the same, right? So we have P positive residuals, right? And we have M negative residuals, and we're going to put those in order, right, over our different time periods, up to n. Right? And so they're going to be here somewhere positive. So this one might be positive, positive, negative, positive, and so on. Right? And if they're independent, the placement of those positive and negatives should be completely random, right? So this is a sequence of positive and negative, right? And there are n choose p, or equivalently n choose m possible sequences. You can either choose where to put the positives and then fill in the rest with negatives, or you can choose the negatives, the minuses, and then fill in the rest of those, right? And so if it's under independence, these should be equally likely, yeah.
Just the notation here, are you saying that it's like a plus and a minus, like, or is that dash like just for each, like?
For each, so these would be essentially the time,
Yeah.
right? And so maybe the first residual is positive, and then the second residual is positive, and the third one's
Okay, but
negative.
the dash below the first two positive signs, that's not a minus sign. it's-
No, that's just a place to put those. So I just have in places and all. So maybe the last one is positive as well. So that the length of whole n is a sequence. And what we, so the placement should be totally random, right? And for each sequence, this test counts the number of runs, right? For each sequence. Count the number of runs of positives and negatives, right? So a run is, a string of positives together or negatives together. So you go positive, that's one run, and then it becomes negative, and that starts the second run. It goes for a while. And then the positive, another one, even one of them, you could have a run of one, and then that's another run, and so on. So you count the number. Right? And positive autocorrelation is you get a small number of runs, smaller than you would expect under just being random. Negative autocorrelation is you're going back and forth faster, so you get more, but often we're concerned with positive autocorrelation. Right? So a test can be done by looking at, if you looked at all possible sequences, what are the distribution of the number of runs, and then the one that you got. And if yours is really small, unusual, then it's not consistent. It's random. And so if you have large n, there's a normal approximation. To the number of runs under independence. So you could look at the number of runs, and if your actual, number of runs for the time order of your real data is down there, it's not consistent with independence. If you have a smaller value of n, so you don't really want to use a normal assumption, you could either calculate all the runs or say you could sample something like 10,000 possible sequences. And compare. And for each of these, calculate the number of runs in the residuals, and compare the actual. Sample 10,000 possible sequences. Right? So this would be under the assumption of independence. You have 30 positive and 35 negative. You just randomly put them in order, count the number of runs, and that would be a random sequence. You do that 10,000 times, and then you look at compare it to the actual number of runs in your time-oriented data. And if it's unusual, if what you have in practice is actually different, then you could, decide that it's not significant, that it's not independent. 10,000 is not going to be, it's not very hard to compute. In something like, if there's 40, residuals, and there's 15 positive and 25 negatives, 40 choose 15 is something like 40 billion, right? So you're never going to compute all of them for a time series that's more than a dozen points or something like that. But so sampling many of them would give an idea of that p-value or a normal approximation would give you a tail area. There are a couple ways of testing. If it looks like it's there, if there's correlation, if it makes sense in the problem, regression, we want to use some filtering to try and get at standard errors, and use that to judge models. Right? So we're looking at some examples of doing this. Right? One data set records the demand for electricity, beer, and chocolate in Australia, I believe, during a certain time period beginning 1958. So the data set is actually just a basic table, and you read it in, and it doesn't have any inherent time series structure. So this particular data set, the number of rows of this chocolate, beer, electricity is 396. It starts in 1958 and is monthly. So there's just some examples. Values, I don't have all the units there. The class of object that it is just a data frame, no time series structure. So you can set up a time series structure for either electricity, beer, or chocolate with this time series command. And once you plot those with that, it shows you the three sequences, right? So electricity, right, is going up with a seasonal pattern, probably becoming more variable as well. Beer is not quite the same pattern, it's kind of this leveling off, right? Chocolate is kind of going up with kind of a little swing, but definitely the seasonal pattern with a trend, particularly in that one or the others. So, and then also it's naturally over time, so we would suspect that possibly there's a time order. Right? If you look at the raw series, this autocorrelation function, you can do that. We don't necessarily compute anything about R1 estimate or the things that we need to use for the filtering from the raw series. Or we have to do residuals first to do that. But anyway, when it's that highly correlated over time, both because of the autocorrelation, but also this changing trend is in the raw series makes it stands out pretty big, right? That these correlations. The second one here is pretty big. There are 396 series, so this goes for 33 years. And we could try to model the time sequence, right? So we need a variable that tells us the time. We could do 1 to 333. Right? Or we could do a sequence that kind of goes 1958 plus 112, right? So that's January, right? And then up to 1991 by 112 would be one way of writing out the months, right? So this little sequence here of months, say the first, here I wanted to show you a little bit of what that looks like, right? So, oops, I must have, those are those months. And some of those things looked like they weren't completely linear, right? They were either leveling off or accelerating, so we want a squared term. Right? If I do a correlation of month with itself squared, it's super high, right? A plot of month versus its square, it's not linear. It is quadratic, but out there, near zero, you can see the bend, but out far enough, you don't see the bend. So we could subtract the average. The mean of month done this way is 1974, 0.542, but that seems a little odd for anybody else to subtract, but relative to 1975, that seems pretty clear. Easy to communicate. So we subtract the month in 1975, and then the correlation between month and then its square or its cube. But a cube is still kind of high, but not as high. Or the squared one is. So anyway, it makes it so it's not so correlated. We're going to predict these different things versus month. Or month squared, so here's a few things to fit those different things. So versus the month has a very significant effect. Right? There's definite trend going up there, but these are the autocorrelated data, right? If there's autocorrelation, it's likely that the standard error is positive autocorrelation. The standard error is likely too small for the ordinary regression output. Right? Same thing for the square. It didn't look so. You can kind of click back through here. You know, is it quadratic? Well, I guess there's enough pattern in there to say that it's a slight curve. If it's not, right? Maybe it's accelerating. Nova says that it's definitely needed there. If you look at the residuals, this is what the residual pattern looks like, but if you put a line through them, right, then you see the autocorrelation pattern very clearly in the residuals. Right? So we're going to use the bigger model with the quadratic. So we fit that model, we're going to take those residuals, and based on those residuals, we're going to estimate R1. Right? So this is the, doing it the kind of so-called manual way. Right? The autocorrelation function on the residuals gives you R1 as well, right? 0.6869, and here's the picture. Right? And since it has that kind of sinusoidal pattern, you kind of see this up and down in the residuals, in the lags. Remember, this is lag 1, lag 2, lag 3, and so on over those. So anyway, we can assign R1 as a value, and that normal test is their autocorrelation. Right, we take R1 times the square root of n, and that's big, right? So we want the tail area above that, so we take 1 minus that p norm, and then that's extremely small, right? We have a correlation that is 0.69. Square root of 396 is almost 20, so 20 times, it's like 12 for a z-score. There's just no question about it. So now we're going to apply the filter to electricity. Right, so we take the electricity at y sub t minus the R1 times y sub t minus 1. Right? And so we only get n minus 1 terms, right? Because there has to be this at least difference of 1. Right? So this little trick takes off the first one. Right? So this is electricity at positions 2 through n. And then this one is electricity at positions 1 through n minus 1. Right? So this one is, the first one here is always 1 ahead of this one. So that does the filtering with this one. We filter month. We also filter month squared because that's in the model. Right? So we get that, filter. Right? And then we regress VT on these two things. Right? And we get these two coefficients, 1.42 and 3. Right? Month and month squared. Wait, what's going on? Summary of, let's see, so month is changed, okay. Let me double check that. And then electricity versus month changed. And summary mod E2. What is going? Oops, I probably have subtracted it twice now. Okay. So just subtract it once. Make sure I'm only subtracting it once. And then run all these regressions. And so the second one, get those coefficients, okay? And then we're going to get the residuals from that one, make sure we get the right things in R1 and so on. And filter, do that right filtering there. And then this one, okay. So 3.5166, and this, where is that one? 3.51, well, maybe there's a little rounding at 99, but pretty much the same coefficients. And these were the standard errors before filtering, 2.9 and 0.038. And then if we kind of keep going, oops, down to these, the standard errors are kind of more than double. It's still highly significant, and there's no question about it, but it's adjusted the standard errors. Right? How much did it adjust them? Well, the adjustment we did for the mean was this. And so that's 2.3, and that's about what it was for that adjustment. Yeah.
So filtering is usually going to increase the standard error?
Mm-hmm.
So why are we going to want to filter then?
So if we use the ordinary regression, it's going to assume that the coefficients, the errors are independent. So when it goes to calculate the standard error, it's going to report this nice small value. Right? Just like when you did y bar, if it's independent, you would use s over the square root of n. But if they're correlated, then the variance is really bigger. Right? So when you're adding together the y's, right, and if they're correlated with one another, then the variance of the sum is bigger, right? Because there'd be the variance of each one plus a positive covariance between them. Right? So by filtering, we take out that effect. So the filtered variables are independent. These are linear transformations, and so you end up with the same regression coefficients, with a little rounding or numerical issue. But in the assessment, the standard error should be appropriate. So it magnifies it, so if it's still significant, it's trying to adjust your value.
We have more confidence because it's not assuming the independence.
Right. If you do this with the other ones, the Beer or so on, so here's the residuals from the Beer series. That, again, it has a sinusoidal pattern, seasonal pattern. R1 is, in this case, 0.49. It's definitely there. If you filter those, and then run that sum rate versus the sum rate of mod E2. Again, the coefficients on the prediction, 2.55, -0.2, are pretty close to 2.4. And then these are the standard errors before filtering, about 0.10, 0.01. And after filtering, they're increased. It's still highly significant. It's a long enough series with a definite pattern, so it doesn't make that go away. But it does that adjustment. Chocolate is kind of the same thing. You do see the p-values go down a little bit. The chocolate one in particular looked like it was, let's see if we can go back to these plots. The chocolate, looks like it kind of goes and kind of like this and kind of going up, so maybe that's, like a, not quadratic, but cubic kind of type of thing. So what if we update that to include the cube term, right? The summary of the cube term, everything is highly significant, right? The autocorrelation coefficient on that model, on the residuals there, is this 0.46, right? And if we filter not just month, but month squared and month cubed, they're still significant, but the p-values have come down a lot. So it's still significant, but does make an adjustment for that. What if you take a smaller series? All right, let's see some example where it really makes a difference and your change included. So I just took 42 values of chocolate and 42 values of month. So here's the chocolate over 42 months, right? And you do, right? Type equals both. You see the lines in there, right, of where it's going. I chose 42 months. Is it suspicious that I've chosen 42 months? Right? Maybe so. Right? It's not a full year. Right? So it's not the full cycle. I've kind of artificially stopped it being high. Just because. I don't know. I played around with it a little I did 36 or 48, but you could be kind of alerted that if it's kind of unequal and there is this kind of seasonal pattern, you've kind of got something artificial in there by the sampling. So if we fit that model with month, there's a significant time effect here. The autocorrelation value, though, is very high on the residuals. Right? So yeah, if you do the significance test there, yeah, there's a autocorrelation structure. So let's filter, and now let's run this. Oh, now it says there's not a significant time effect because the standard errors have been inflated. So the estimate, the slope was supposed to be 1.75. Changed those numbers some. Importantly, it has changed the coefficients, so not exactly sure why the numbers have changed. Maybe it changes more on smaller series. But anyway, it has produced something here that has very little, it's not, actually on these data, it looks kind of flat. 175 seems like a big value, but the scale over here is in the thousands, so it's just kind of a little change. Right? So in some cases, it might make some of those effects go away. Right? So for this one, we did that normal test, right? That was the p-value there. And so there's a very strong correlation. But how can you do this runs test to see if these, right? So there's a package called random tests. There's other packages that do randomization tests. So where would you find these things? Well, just in Google, if you do runs test in R, it runs test function packages. Looks like a different time series. Waldorf runs test. This is the one that I was looking at. This runs test is there. Where is this? In rand test. Rand test is the package that's there. One place to look for these rand tests at CRAN. CRAN is this comprehensive R archive, right? And so RAND test is a particular package, right? It has a reference manual that describes some of the things that are on there. If you want a hard copy, a PDF copy to look at these things. This randomization test has a bunch of different functions. Some data sets like sweet potato data, and there's another one somewhere. But anyway, there's a runs.test command, something for doing permutations, so it's kind of packaged together, this rank runs.test, Wolfowitz runs test. Walls and Wolfowitz, two people back in the 1920s, 40s, who had a big influence on development of mathematical statistics. And so there's something there about this, right? What results it gives, and some references, and an example. So they have 23 determinations ordered in time, the density of the Earth, and they do this. What this one does is it compares to the median of those points, right? Is the values you see are below the median, right? So it gets a run and then judges, are the runs that you see, the number of runs, more or less than you would get from random. If you install this package, so under packages, and you want to install a package, rand tests is there, and it would install, and then type library of rand tests, You can do help of the package to see what's there, and you could also type help of runs test, and it will give you that same help file that was in that PDF. So you can access all that information within R. Or find it in print. When you run this, right, the runs test tells you the data is this. It comes up with a statistic, which is kind of standardized version of that, the number of runs. It says there are 10 runs, 21 in one group, 21 in another group, so 42 and off. And the null hypothesis is that they are independent. And the alternative is that there's some non-randomness, like a correlation. Where do they get the number of runs? Well, if you look at the data, there's a sign command in R which returns +1 for positive values and -1 for negative. Right? So here's the 42 time periods, right? And the negative ones are the signs of the residuals. So the first couple of residuals end up being negative. Right? We'll do a plot shortly. Right? And so the first run, you start out negative, and then at the third one they become positive, so that's the second run. And then a negative, so that's the third, and then fourth, and fifth, and then sixth, and seventh. And at the end, it just kind of barely dips below the median, so it becomes, or just barely goes above it, then down, then back up, so we get a couple more runs right there. And if it was truly random, the chance of having, so many in a row of one type is rare, right? So if we had a big number of observations, it'd be about 1/2 for positive or negative. So 1, 2, 3, 4, 5, 6, 1/2 to the 6th is kind of small, right? And to have a number of these where there's that homogeneity is kind of unusual. Right? So when I initially looked at the residuals versus 0, right, there were only 8 runs. It took me a little while to figure out what was going on. How was it getting 10 runs when I only see 8 changes over time? Because when you do it versus 0 rather than the median, that one's also positive. Right? These residuals at 39, 40, 41, and 42 are all above 0, but one's pretty close to 0, and the median is just above, happens to be just above 0. The useful thing that if this worked here is this plot shows you the 42 observations and then where it has broken it into runs. So it's kind of a neat little graphic. And it shows you the median line there that it's doing reference to. So the plot actually kind of helped me understand what it was doing. So our book does it versus 0, whereas it's implemented, it can be implemented versus any reference, and it does it versus the median. Versus the median, it splits it into 50-50, so 21-21 balance. If it was versus 0, it would be 24-18, I think, which would still work. So that's the signs that are there. Right? So anyway, this test ends up giving that very small p-value, so definitely there is some autocorrelation there that needs to be taken into account. I'm not going to try to make that plot. If you do get into time series, right, we could look at other relationships between series. So you can use one series to try to predict another one. So your x's become one series. And so there's this air passengers data set in R. That's just random stuff. That starts in 1949 and goes to 1960. Right, our beer and chocolate and electricity started in 1958. It goes much later. But they do overlap in a little part. Right, and there's a ts.intersect command where you can take two series and take the places where their dates overlap. Right? So there's special functionality. We're not going to get heavily into it, but in a time series class, you would learn, or that's where you're going to do work. So this AP electricity, they have some dates in common, 1958 up to the 1960s, so 3 years where you get airline passengers and electricity, both in Australia, I believe. So you can pull out just the AP, the little dot I means where they intersect, and the electricity ones. This is the airline passengers over time. Kind of some growth during this period with big seasonal variation. How about electricity during this time period? It's kind of, electricity has seasonal variation, and electricity also has kind of this growth. Electricity cost or usage is also going. Underlying both of these can be population and technological economic advancement, but they're kind of, it's interesting that they're kind of similar. If you try to predict electricity versus that, right, here's the, plot. Well, here it is a vector that I can add a line to it. And there's the regression line. If you use electricity to predict airline passengers, right, the electricity cost or usage is kind of the entire economy, kind of a bigger thing. Airline passengers is a particular feature maybe used, like, which is more stable and kind of universal to predict the more particular thing. That's what I was kind of thinking. I don't think I need, oh, if you put the line, where is the line? Oops. Yeah, they're not really ordered in time, so that doesn't help you. You get this funny thing because the electricity is sometimes up or down, and so it connects points, and so because it's seasonal, like, you can't really kind of do that. The scatter plot works fine, the time series works fine, or this plot that we had from before. The correlation between these things is pretty high. If you try to model these and fit the model, there's a significant association. Right? That is their autocorrelation in these residuals. We know that the things are going over time, so you can get the residuals, that the first autocorrelation lag 1 coefficient is 0.26. These little lines are at that significance test. If you did the p-value from that normal test, it's 0.117. It's a little bit smaller. It's not quite significant, the autocorrelation in this particular subset of the series. And for this model, right, so it's relevant to the model. And then if you do the runs test for that one, you get a similar p-value, 0.09. Not significant. So that would suggest there won't be much difference in this, statistical assessment in this model if we did the adjustment. But it suggests that electricity demand and usage very well could predict, right? So if you had ways to model that over time, and you had some idea of how things were changing, or the data for that came out in advance, and now you want to, what was the summary for the airlines? Maybe it takes a little while to get that together, whereas the economic, the electricity could be measured more in real time. It could be useful. It would suggest you'd have a way to predict. Now you might want to do things much more sophisticated. On Friday, we'll try to talk about a couple extensions. So obviously we see that sinusoidal thing in there. These models that we're doing are not capturing that. It's just getting the big trend. So we'll see a few ideas of decomposing time series in different parts. Next.